Hello everyone, my name is Martin Doyhenard. I'm a security researcher at the Onapsis Labs, and today I'm going to present a new set of techniques that can be used to obtain control of the response queue in a persistent connection by exploiting HTTP Desynchronization vulnerabilities. So the agenda for today: first, I'm going to start introducing the concept of request smuggling and what is HTTP Desynchronization. And even though I expect that most of you already know what HTTP smuggling, request smuggling is and desynchronization, I'm still going to make a quick recap. And I'm also going to talk about desynchronization variants, in particular one that was found and reported to many vendors that will be used in following demos and examples. Then I'm going to start talking about response smuggling and how to desynchronize responses and the response queue, and how to also obtain response concatenation to create new payloads and to cause what I call response scripting, which will allow me to exploit the browser of the victims, and also to cause arbitrary proxy cache poisoning, which will allow me to also persist the attacks, which in the past was impossible. And finally, I will present some demos in some labs and also in one of the most used ERP in the world. So, what is request smuggling? The idea behind request smuggling is to exploit HTTP desynchronization vulnerabilities, and this kind of vulnerability was introduced or discovered in 2005 by Watchfire and reborn in 2019 by James Kettle, who presented a set of methodologies that could be used to exploit in a much more reliable way this kind of attack, this kind of vulnerabilities. So the idea behind, again, desynchronization is to abuse the discrepancies or the differences that parsers in the front end and the backend server has. And in particular, these differences are related to the way that the parsers can find or can calculate the length of the HTTP message and the body of the request. So if I'm able to cause this difference or cause these discrepancies, then I will be able to split a single message that will be forwarded by the proxy into the backend, and the backend will consider this as two different parts and will allow me to affect the victim's request and to place a prefix that will maybe execute something in the backend or cause some execution also in the browser. So a simple example, let's consider we have a proxy and a backend server. The proxy will only take into consideration the first content length if I send multiple content length headers, and the backend will only take into consideration the last content length. This is something rather common in many servers and in many proxies, because they have to choose, in some cases they will not allow this, but in many cases they will choose one of the content lengths and will use it to calculate the length. So in this example, I send the following payload containing two content lengths. The first one, it will be used by the proxy, so the proxy will forward the entire message to the backend, considering that it's only one single message. But when this payload reaches the backend, it will be split in two because the second content length will be used, so it will consider that only 5 bytes are in the body. So only the first 5 A's will be used as part of the body, and then the rest of the body will be used as an entire new HTTP request, which in this case will be a prefix because it's not completed. So when a new request reaches the proxy, which in this case could be a victim's request, it will be also forwarded to the backend, which will be concatenated with the previous prefix that I injected, and therefore what will be executed instead of get to my account that the victim issued, the backend will think that the request is get to delete my account. And in this case, we can see that it will use the cookies and the session ID. And so probably the account of the victim will be deleted. But also the response of this request will be sent back to the victim. So if the response contains any malicious payload, such as a JavaScript, this will be executed in the victim's browser. So we will see many of these diagrams because it's easier to explain many concepts. And the idea again is the attacker will send a single request that will be forwarded entirely by the proxy. The proxy will think there's only one request. The backend then will be splitting this request in two. It will create a response for the first part, and it will be sent back to the attacker. But then when the victim or the client sends a new request, this will be forwarded again by the proxy, and the backend will concatenate it with the previous injected prefix. It will create a response, and the response will again be sent back to the client. So that's the main idea of HTTP request smuggling or desynchronization. We will see later how to exploit this or how to exploit using request smuggling. But as I said, we can use for example, two content lengths, but also there are many ways of creating this desynchronization. One of the most interesting variants that are called, that I found, and I was able to report this new variant to many vendors, was to use some new connection headers that will allow me to exploit this kind of vulnerabilities. So the idea is, in many previous examples, we were using an issue, or we are exploiting an issue that exists because of the implementation of the RFC or of the parser. But there is also another way of exploiting this, and it's to use the RFC and to use some concept that when the HTTP RFC was written, they were not considered. And to understand this, we first need to understand what is a end-to-end and a hop-by-hop header. So an end-to-end header is those headers that are intended to go from the client to the backend and forwarded by any proxy in the middle. The other way is the hop-by-hop header, which is not intended to be forwarded by all the proxies, and instead, when the proxy receives a hop-by-hop header, it should process it and delete it, and then forward the request without this header. Okay? So we can declare this using the connection header. Most of you already know the connection header, and it's used to establish directives such as close or keep alive to say how the connection should be established. But it's a more general purpose kind of header, because we can use it to set any other custom value, and then this value will be searched in the headers and deleted when the request is forwarded. So, as an example, if we send a request saying we have the connection keep alive and the option value, then we can set a keep alive header to say how many times or how many requests should be used in the same persistent connection. But also we can set an option header, which is the value we set in the connection. And what will cause this is that the proxy, before forwarding this request, will delete the option header and will delete the keep alive header, as well as, of course, the connection. So it's not interesting as using with a keep alive or a close, but what if we, instead of setting a keep alive or a value that is expected, we set some value that is expected to be an end-to-end header. For example, the content length. So if I send this request to a proxy, the proxy will think that the content length is 13 bytes. It will forward the entire request, but before it does, it will remove the content length header and the connection header, because it thinks it's a hop-by-hop header. So when this reaches the backend, the smuggled data will be considered to be another request, because the content length is not there anymore, so it will consider it to be 0. This vulnerability was reported to Google and to many other vendors, and in this case, Google was vulnerable in all their domains, and I was able to prove that we could hijack any user account or any session cookie using this kind of attacks. Okay, so how we can exploit these kind of vulnerabilities? We said we can modify the request of a victim so that it causes some different effect for using their cookies. But there are also other kind of attacks, like for example, bypass a front-end control. This is, we can bypass some authorization controls in the proxies, because we can hide some request from the control, because it will not consider the smuggled request to be another request. So it will not verify that, for example, if we try to access to a URL that it should be forbidden, this won't be verified by the proxy. Also, we can upgrade existing vulnerabilities, such as XSS, open redirects, and other kind of vulnerabilities that require for user interaction. And that is because we can hide our injection, our XSS in the smuggler request, and this will cause that the response is the response for the victim is modified, and then the browser gets exploited using these kind of attacks. We can also hijack requests, victims' requests, where if we are able to store the request using some kind of storing and retrieving features, such as an email, we could use the prefix to be a request to one place that we can later retrieve the information. And we can also cause some other kind of attacks, such as server-side request forgery, for if there is an internal redirection supported, or other kind of more interesting attacks, but are much more complex. So this is all request smuggling. And why do we need more research about it? It seems like we can exploit everything just with this. But the truth is that there are some issues with the way that James Kettle presented to exploit these vulnerabilities, and they were presented in the past. And this is bypass front-end controls means that we only can bypass controls that are in the proxy, not in the backend, and that's rather uncommon in many applications. We can also upgrade existing vulnerabilities, yes, but we need to have extra vulnerabilities before. So if we look for an application and we find HTTP desynchronization, but we don't have any other vulnerability, then this won't work. We can also hijack requests, yes, but only if if we can store data and we can then retrieve this data. And this feature is not so common in many applications. And also, in many cases, we will need to be authenticated. And again, we need many preconditions, and it's not so reliable, the attack, so the attack complexity is quite high. And finally, it's not persistent. We need to keep attacking the system to exploit victims and to get the responses. So to get the requests. So I started looking for other kind of attack vectors, and then I started thinking, well, if I'm able to smuggle a request in the request queue, then I am able to smuggle a message in the response queue. And the answer was yes. But to do so, instead of injecting a prefix, I will have to inject an entire request that is completed by itself. Okay, it won't need another request from a victim or from the attacker again. So in this case, as I said, I will use the same kind of ideas, but I won't inject a prefix. I will inject an entire request, which is completed. And in this case, we can see that if I send these two requests or this smuggler request, then this will cause that the backend recreate two responses. Okay, so one request was issued by the attacker, and two responses were created. And what's interesting about this? Well, if then a victim issues a new request, the proxy will also forward it, but it will think that there are only two requests issued. So the first response will be sent back to the attacker. The second response will be sent back to the victim. And if the attacker sends a new request, he will receive the response that was intended to go to the victim. So that way, I'm able to hijack different responses that are not intended for me, but for other victims. These responses, in this case, if I hijack a response to a login, I will probably hijack the cookies of the session cookies that will allow me to obtain control of the victim's account. Again, using this diagram, we see that the attacker and the client sends both requests. The proxy thinks that there are two requests only, so it will forward them to the backend. But the backend will split them and create three different responses. So when these three responses go back to the proxy will send the first one to the attacker. The second one, which was injected by the attacker, it will be sent to the client. And then when the attacker sends a new request, he will obtain, as I said, the victim's response. But if we try this attack, we will see that it fails. And this is because the connection keeps closing it. And we can understand why if we consider how pipelining works. So when a proxy receives these two requests, it will send the first one through one connection. But instead of sending the client's or the victim's request, if it was received at the same time through the same connection, it will establish a new connection, and therefore the message will be sent through this connection, and it won't be affected by the attacker's request. So again, the three responses will be created, but in this case, the client is, as I said, is not affected, so we cannot get the client's response nor to modify the client's request. What's more, when the proxy receives an extra response, it will think that this is a connection error because he only issued one request. So for each request the proxy issues, it should receive one response, not two. So this will cause that the connection gets closed and the attacker's injection gets lost. So how can we solve this problem? So the real issue here is that the connection is being closed, because if not, a following client's request will also be forwarded through the same connection and it will work. So the idea is the attacker will send a request that will be splitted in the backend, but in this case, the second request will take some time. We will call it a sleepy request. Now this time doesn't need to be a long time, it just needs to allow the attacker to receive his response and the proxy to receive a new request from a client or from a victim, which will be again issued to or forward to the backend. And now the response that was injected can be forwarded back to the proxy. This will cause that the client receives this injected response. And when the attacker sends his new request, he will, in this case, receive the victim's response. If we use another kind of injection, which is what I said, a sleepy request, we see that this attack gets successful. We are able to hijack a lot of responses. And so we have fulfilled we have bypassed this issue and we are able to hijack responses. So this is not quite interesting. It was not known, but it's still hard to exploit. So what I wanted is another way to actually create new payloads, because I still have the same issues. I am able to hijack responses, but I have the same issues as not being able to create attacks with like XSS if I don't have an XSS. So now, if I can smuggle one entire request inside my carrying message, I can also smuggle two requests. So in this case, I will show how to use the same ideas or the same attack to hijack a request from a victim. And this is without any storage feature or without having to retrieve any data. So the idea is we will use a reflection and then a desynchronization to obtain the victim's response. In this example, we send one request that it will be forwarded by the proxy. The backend will receive this and split them into three different requests. The first request will create a response that will go back to the attacker. And now the proxy will be able to receive another request from, for example, a victim, and will forward it back to the backend. When the backend receives this, it will concatenate it with the last request. And now the sleepy request create a response. This will go back to the victim, as we already saw. But now the extra request that was injected in the backend will use the request that was issued by the attacker, by the victim, to reflect it and to reflect the content. If you see, I use a big content length here, and that is to allow the attacker to send extra data that will be also concatenated, and to avoid that the backend creates the response before the new data is retrieved. So what this will create is a new response containing the request of the victim, but as I'm able to desynchronize this, the attacker will then receive this response. So again, not so much interesting. I want to do something more. I want to create new payloads. So this is when I started looking for concatenation and to desynchronize something else. So until now, we are able to desynchronize the request queue, okay, by using different content lengths or by using a transfer encoding. But is it possible to desynchronize the response queue? I know that I cannot control the content length because, well, the content length is created by the backend. So it's impossible for me to actually modify the content length so that this gets desynchronized. But are there any kind of requests or maybe responses that use a different way of calculating the length? And this is true for head responses. So, and for head requests. So, if I issue a head request, the proxy will know that the response should not contain any body. But the RFC allows both the backend and the proxy to establish a content length that will not be used. So, for example, this is a GET request to Google, to a not found to any place in Google, and if we set a GET to, let's say, AAA, we will see that we receive a response with a content length of 1,557. But if we issue the same request with a head request, we will be able to receive the same response, only the headers, but the content length is still used. So the idea is the proxy knows that he issued a head request, so it won't consider the content length. And there is no problem using this. But what if we are able to cause that the proxy fails to match responses and requests? So are we able to cause that the proxy believe that it issued a GET request when it actually issued a head request? And the answer is yes, we are. And we are because we are using this desynchronization attack. So if I send a GET request containing two smuggle requests, the first one using a head and the second one using a GET, this will cause that the backend split them into three. Now, the proxy, remember the proxy only sees one request, so it thinks that it issued a GET request to the backend. So the backend will respond the first one, and this will be sent back to the attacker. But when another request reaches the proxy, it will forward it, and in this case, it's a GET request. So again, the proxy thinks that it had issued a GET request when the backend will respond to a head request. So when the proxy receives this request, it will consider the content length to be valid, and it will wait for 50 bytes extra, for 50 extra bytes. So when the next response is generated and is obtained by the proxy, it will use the first 15 bytes as the body of the first response. And this will be sent back to the victim for his GET request. Now the extra bytes will be used as another response, which in this case is a not a valid response because it's not using the HTTP beginning bytes. So this will be discarded and the connection will be closed. Again, let's see this in an example. We have an attacker who sends his GET request containing his two smuggler requests. The red one, remember, is a head. This will be issued or sent back to the backend. The backend will then create 3 responses. The first one will go back to the attacker. There's no problem here. Now, when the client sends his GET request, the proxy will forward this and think that there is a GET request in the request and response queue. So when the responses reach back the proxy, the first one saying that the content length is different from 0 will use the next part of the response as the body, and therefore this will be forwarded back to the victim. Now, as I said, the extra bytes will cause that the proxy close the connection, but we don't care about this because we already achieved that the client received this new kind of payload. Now, what can we do with this? Well, we can build new payloads using headers and bodies. So the headers will be set using the head request, and the body will be set using the next request, the next response, which in this case will also use the headers of this response as part of the body. So we can modify the content type, for example, by saying if we have a response that contains a reflection or something that we can use as an attack, but it's a plain type, then we can modify this by setting a new header to this response, which sets the content type to be text HTML, for example. And also we can use headers as bodies. So if we have a reflection in the headers, such as an XSS, then, which wouldn't be a vulnerability in other case, then in this case we are able to use it as a script. So again, if we are able to use a head request that generates a content type text HTML and a content length of 100, and then we generate another response that uses, for example, in the location, a reflection which is a script, which is a JavaScript, this will be used as an actual JavaScript instead of headers. And we will be able to exploit the victim browser using this attack. So I will show a demo using this. And the idea is we are going to have a varnish proxy and an NGX backend. Okay. So, yeah, it's everything here. So I created this small example. We have this page, this hello smuggler page. We also have a redirect URL, which is if we send anything, well, this can fail. It will also send back to the home. So let's see this in Burp. So again, I have my get hello world to hello smuggler. It's just a static response. Nothing interesting here. I got my get which will generate a redirection. But here, if I use, for example, one thing that is pretty common, I can reflect data here. Well, XSS should be. I can reflect data here. So I could set, for example, a script. And this will cause that the application returns a redirect with a location reflecting what I injected, which is a script. Now, this is not a vulnerability by itself because I cannot do anything with this. But remember, we have the get hello smuggler, which can be converted into a head response, to a head request. And as in many cases, the content length will indicate that there should be body, but any proxy in the middle will say, okay, this is a head request, so I'm not expecting any body. But then, if we send this request, this is the carrying request. This is the head that will produce what I said. This will produce that a response containing a content length different from 0 to be set. And then this will be concatenated. So I can send this request, and the next request I send will contain, instead of what is expected, will contain the payload. It will also contain part of the response of the victim, and it contains the head response, which indicates that it should use the first 383 bytes as part of the body. So I can use this to keep modifying the responses. Here, I'm not throwing the attack, but if I go in Burp and use the True Intruder, which I already said, okay, here I will keep sending the attack. I set a timestamp so that my own attacks don't affect the attacker. So the attacker doesn't want to receive the malicious responses. So if I start throwing the attack, next time I go here and I said, hello smuggler, I get the cross-site scripting. Okay? This will work for any URL, or should work for any URL, I hope. Yeah. And we can see that we will keep receiving this kind of responses, these payloads, until I stop the attack. So this is not a persistent attack. If I then send the request when the attack is stopped, I will receive what I expected. Okay. I'm having some issues here. The internet. Okay. Some issues. Okay. So as I said, this is not a persistent attack. I'm able to modify the responses, but only if I keep sending these attacks. So is there any way to actually send one request and modify the responses for all the victims in the future? And this is possible by using the cache control header. So remember, what I'm doing here is to build a new payload by using headers and body. I can choose any response or any header's response, and then I can set any body I want with other responses. So instead of looking for some response that contains a content length and a content type HTML, I will also look for a response that contains a cache control header. This will cause that the proxy believe that the response should be stored in the cache for the request that the last request that was issued by the proxy. So again, if I send this kind of attack where I'm doing exactly the same thing, but in this case, okay, the attacker will receive his response, and in this case, the first response or the header response will also contain a cache control. So when the next request is forwarded to the backend, this will again produce the payload, but in this case will be stored in the last request. So this is to redirect. So the next time a victim issue a request to redirect, he will receive the same stored payload. Okay. So, and again, the same diagram. An attacker, in this case, the attacker will send two concatenated requests or two pipeline requests that the proxy will recognize as two different ones, and that this is because we want to set the target URL that will be poisoned for the one that the attacker chooses, not the victim's one. So now the backend receives these two requests. It will split them into 4. The first 3 that were smuggled and the last one that will be used as the target. This will create 4 responses that will be sent back to the proxy. The first response will be sent again to the attacker. Now the second response, which contains the payload, will be sent to the next request, which is a GET request, again to from the attacker. But in this case, the request the proxy will see that the response contains the cache control header. So it will store this in the cache, and then for the rest of the message, it will be discarded because it's not a valid HTTP message or HTTP response. Now, when the client sends a new request containing the same URL, the proxy, instead of forwarding this to the backend, will look in its cache, and it will look for the response that was stored. So the client will receive this payload anytime the request is issued. So we are able to poison the web cache of any proxy, and we are able to poison the web cache of any URL that we arbitrarily choose. And also, as I said, the response can contain any payload we want. So again, I have a demo. I will use the same system. But in this case, instead of sending many requests, I will only send one. So I also set a new endpoint, which is this cacheable endpoint. If we see this in burp, we see that we have almost the same response that in the hello smuggle. But in this case, we have the cache control header. Okay, so the cache control header will cause that, as I said, the proxy thinks that it should store this in the web cache. Okay, we see if we send this, we will be storing this. So now, if I send the same kind of attack, but instead of using the hello smuggler, I use the cacheable head request, this will cause that the response gets stored. Let me check this. And if you see, I'm actually sending, this request is not smuggled, okay? So the two smuggled requests are this. We have 138 bytes, which is the content length. And the last one will be used as a pipeline request. So I can set any URL I want. Let's say I set this URL. This will poison the index, let's call the starting point URL. So now, if I go here, I will receive the payload anytime I send a request. I can also poison any other URL, and I can even poison URLs that does not exist, that should give me a 404. So for example, let's say I send ACSD. Then when I make a request to ASD, again, I will receive again the payload. Okay, so finally, I want to show that this is possible in real systems. So I established a small lab, but you might say, okay, you are doing some tricks, and this is not possible to do it in real cases. I was able to do it in Google, but I'm not able to show it. But I am able to show SAP because I do have an old version of SAP. So the vulnerability in SAP was kind of different. It was that when first the SAP have two important components, which is the web dispatcher. The web dispatcher is a load balancer or a web cache proxy, can be used also. And the thing is, when I send a request to the web cache, to the web dispatcher containing a transfer encoding, and the transfer encoding is not just chunk, it's an invalid transfer encoding, the web dispatcher will convert this to a chunk message, to a transfer encoding chunk. But this is not true, or it will not convert it, it will not forward it like this, but it will consider that the transfer encoding is chunked. But the backend, which is an SAP for S/4HANA, which is the new flagship ERP solution of SAP, and it's an HTTP server. This also works for other SAP HTTP server versions. In this case, the transfer encoding will not be converted to chunk, but instead it will be considered to be identity, which is the same as saying, hey, let's only use the content length. So I can build a new payload using, as I said, response block, which is the headers. In this case, I will use the hit to reset password, which will return me a response containing the content type text HTML, a content length, which is different from 0, and a cache control header, which says that the response should be stored for a week. And then, as the body, I will use a similar example that I use in my own lab, which is a get containing the parameter xsub origin location that will also create a response containing the payload that I can provide, which is a reflected parameter, and will be reflected actually in the headers. So this is not a vulnerability by itself, but I will turn it to a vulnerability by combining this with the headers. So again, I send a carrier request, which is the attacker's request that will be sent to him. And I will send the transfer encoding using the attack that I just described. This will cause that the proxy forwards the first part to the backend as an entire request, and then the next request, which is the pipeline request, will also be forwarded, but as a different request. When the backend receives this request, it will split them into 4. The first response will be sent to the attacker. The second response will contain the content length different from 0, and it will not be recognized as a hit response because it matched the get. And it will match the get to the target URL, so this is going to modify the target URL in the cache. The body is generated using this get request that produce an XSS. And finally, the last response is the one to the target URL, which in this case will be discarded. Now, as I said, this response, the first response is going to be back to the attacker, and the second response is going to be stored in the cache for the target URL. So we will see a video demo. Again, we can see that if we go to SAP, we have everything as expected. We can send this head request to reset password, which will generate this response containing a content length, a content type, which is HTML, a content length, which is different from 0, which is something that the RFC allows, and a cache control saying that the response should be stored for a week in the cache. Then I will also show how to generate the payload. The payload is again stored in the headers of the response, which is not a vulnerability. In this case, I'm using an alert to cache XSS. And the content length, or the length of the body of this entire response, corresponds to the same length of the content length that was in the head response. Now, again, I use the attack using the invalid transfer encoding. I use the content length to be 5 bytes, so that only the first 5 bytes are used as part of the first request. Next, the head request will create the headers. The payload will be created with the get to the redirect response. And finally, the target URL will be the one that will be poisoned. Okay, this is the first request that will be forwarded, the second request that will be forwarded by the proxy. And now, when I send this request, the proxy or the web dispatcher will modify the cache for this same page, for this URL. So when I say it again, I get the payload. This way, I can modify the response for any victim, and I don't need to keep sending the attack. I only need to send one request that will modify the responses for a week. I can do the same with the login page. Remember, I can set any kind of payload. I could also set something different, such as a fake login, so that the victim sends me his credentials. In this case, I will inject a malicious JavaScript in the login page. Okay. And again, now if I request the login page, I will receive the payload which executes this alert message. Okay. I have time to show this. Okay. So, to solve this, SAP released 2 security nodes, and it marked this as a CB 2021, well, this number. So I'm also able to do something else with the rest of the response that was being discarded. Remember that when I was using only the first part of the second request as the body, I had some extra bytes that will be discarded. But what if instead of using this byte to close the connection, I use them to create a new response? So again, let's say that I send this request to the backend server, which will it will be forwarded as one, but will be split into 3 different requests by the backend. The first response will be sent back to the attacker. The second response will be used as headers. And now this response, let's say I'm able to inject this or to reflect this in the response. This response will be used as part of the body. So the first 100 bytes will be used as part of the body of this hit request. This will be forwarded back to the attacker. But now the extra bytes, which were reflecting the parameter that the attacker sent, will create a new response. In the past, we would have a response that wasn't invalid, so this would create a closed connection. But in this case, this response is a valid response or a valid HTTP message, so it will be also delivered back to the victim or to the attacker. And this will allow me to actually create any kind of response, not using blocks like before, but to actually write anything I want. So in this case, I will use a response that contains a cache control, a content length, and an arbitrary body response. And this will be sent to the example and will be stored in the cache for the example URL. Okay, so some final conclusions. The idea of response smuggling is that we don't need to rely on any extra vulnerability, and this is true for all systems that I had looked, because I'm not looking for vulnerabilities. I'm looking for things that are not considered to be invalid, and I rely on the RFC. I use, for example, the content length to be something different, and that is valid by the RFC. Also, in this case, I will analyze how the scoring should be for this kind of vulnerabilities, and if I'm able, this response smuggling will be able to, I will be able to perform response smuggling anytime I have an HTTP desynchronization vulnerability. Okay, so I don't need, as I said, any extra preconditions. And using response and request smuggling, I am able to hijack messages, so the confidentiality is completely compromised. I'm also able to poison the web cache or to inject nested responses that are invalid, so I'm able to compromise the availability by setting, for example, responses that says 404. I'm also able to compromise the integrity because I am able to persistently modify the responses that a server or a proxy will give to clients. And as I said, using the cache technique, I'm able to persist this attack and to compromise any client that will use this application. And finally, of course, to hijack different requests and responses using the sleepy request technique, I'm able to increase the reliability not only for response smuggling but also for request smuggling. So in the future, this kind of vulnerabilities should be considered as critical and not as medium as many bug bounty programs would say they are, or as many other vendors would consider to be. Okay, questions?
First of all, thank you for that. It was really, really interesting. Can you hear me? It was really, really interesting, and thank you for that. I just want to ask a couple of questions.
Yeah.
So, when you send the head request, it has to be, when you send the head request,
yeah,
it has to be, the response has to be 200 okay, or it can be different.
It can be anything. The only important thing is that the connection is not being closed. So, for example, if the response is a 404, in some cases that will close the connection. But in most cases, no, that's not true. Only for example, in SAP, it would close the connection. In Google, no.
For example, like a 401 or
you can set anything you want, and this will work, and it will even be exploitable because the browsers will just check that it's a 401, but it will still display the all the payload, and so the browser will execute the JavaScript.
Cool.
Yeah.
And did you try this attack with web application firewall on the web app? Does it matter? Does it make a change?
It doesn't matter because it actually helped me. There are some. I tested with one firewall actually, and it helps because firewalls are still HTTP proxies and they follow the same rules, and they don't verify this because they cannot look for vulnerabilities that are not vulnerabilities because.
Yeah, but sometimes they see the string like you did script alert script within the body, and they block it even with the start of script or start the script of end of the script.
But in many cases, so the examples I showed was using the attack in the headers. But you can also use this in plain text. So many responses that set plain text as the content type, you can use this to create new payloads that will change the content type. Okay. And the firewalls won't verify this because they think that this is safe. I mean, there are many ways of bypassing firewalls because there are safe ways, or they would think this is safe when this is not safe actually. Cool. I can also bypass the firewalls by smuggling twice the request.
Oh, nice.
So that the firewall will not recognize this because it will not see a request actually.
Yeah. Cool. So and the last question is:
sure.
Did you find it on different besides like Google, as you said, and SAP and Varnish? Did you find it on other?
Yes.
You can say.
Yeah. Okay. Some of them are still working on it because they first. So the problem here, and why I said this conclusion, is because many of the vendors would say, okay, HTTP desynchronization is not a big deal for us. So I had to prove them that with just one request, because even when I said, okay, here, one request will modify your entire application, they would say, no, it's impossible. So you have to prove it, and sometimes in web applications that are public, it's hard to prove it without modifying and having some issues.
Yeah, okay. Thank you very much.
Thank you.
Thank you.
There was another question. Thank you.
Hello. Okay. Thank you for presentation. I have only one question. What was in a skip it slide and why you skip it? You hear me?
What? Yeah, no, it's... There's no?
Yes? No?
Yeah, I was hearing another thing.
No problem. Okay, thank you for presentation again. So, I have only one question about what was in skip it slide and why you skip it.
No, I thought that I wouldn't get with the time. So the skip it slide was the arbitrary injection, which allows me to create new kind of responses, actually to write the response in the entire by using the last part that is, so remember, when I use a head response, it will take the first X bytes that is set in the content length, okay, of the next response. But then the extra bytes that are not used as the body are in many cases discarded. But if I'm able to reflect something there, so for example, a response which would say HTTP 1.1, anything else, 200, let's say, I'm able to write a new response and use this to actually create responses by scratch, not using blocks, but by writing it by myself. So this would allow me to create even better payloads, and even when I was able to prove this, in one vendor. And this allowed me to create a payload that contained a JavaScript, and in any other way it was impossible because they had like almost nothing reflected, almost no way of creating a new payload. But this way I was able to create a payload from scratch and inject it in the cache.
Okay, thank you.
I think we're running out of time there, so thank you very much, Martin, for your talk.
Thank you.